Hi, welcome to workshop 4 on data structures and algorithms. In this workshop, we'll be talking about recursion. Recursion is very important in developing algorithms. In fact, in most of the works we'll be doing and during the lecture after this particular workshop, we'll be using recursion to develop algorithms. Because of how large this topic is, we will not be able to finish it in one section. So we'll be talking about recursion in workshop 4 and also in workshop 5. Here is an outline of what we intend to cover during this session. We will talk about the concept of recursion, such that at the completion of the session, you will be able to think recursively and also demonstrate an understanding of recursive methods. We'll also be looking at how you can use recursion to write algorithms and how we can trace recursive algorithms. We'll also go further to talk about how you'll be able to recognize tail-end recursion and know how to remove the recursion. We'll be comparing recursive and iterative techniques. And lastly, we will apply backtracking techniques in the solution of problems. Just a little bit of the background on recursion. Before now, we have been using loops and for loop and while loop to repeat a section of code in the algorithms you have been developing. But this section of code being repeated can also be done using a recursive approach. So recursive is an alternative to repeat a section of code. However, one must be very careful when using recursion to repeat some sections of the code because of some pitfalls that recursion has. We'll be looking at these pitfalls or the dangers of using recursion while we progress in this lecture. Before we continue with the lecture, let's look at examples of recursion in real life. The first example we'll be looking at is the famous captain story. The famous captain story goes this way. It has that it was a dark and stormy night, and the captain said to the mate, "Tell me a story." So the mate began. So the mate began and continued telling the story. But the story kept repeating itself again and again and again and again. So the story has no ending state. It continued repeating itself, but it has never ended. Another example of a real life example of recursion is this song that has different stanzas, but eventually got to a point where it needs to repeat itself again and again. This is also similar to the previous example that we gave. We have an activity here which asks us question: what do you observe about two examples we've given in the previous slides? The observation is that the examples repeat themselves again and again. And do you see any problems? Yes, there was a problem of continuous loop without stopping. And we have a question, the next question, which says, what would happen if you write a program like this? If you eventually write a program like this, you will know that that program will never stop because it has no stopping condition. The program will continue to loop forever. Let's look at another example of recursion in real life. This example of recursion is the Russian Matryoshka doll. On the Russian Matryoshka doll, we have 5 dolls here, but 4 of these dolls have holes under it. And this doll works in a way that you can use the bigger one to cover the smaller one. So this bigger one can cover the smaller one, and this one can cover the next smaller one, and this can cover the next smaller one, and this one can cover the smallest one. One important thing to note about this operation is that it is happening recursively. Another important thing to note is that it has an end. It has an end because the smallest does not have any opening on the bottom. So there is no other smaller door that can go under it. So at that point, it stops the recursion. The recursion techniques ends or operation ends there. So what is the difference between this approach and the previous 2 examples we have seen? The major difference between them is that this one has the stopping end or stopping condition, such that as we see, that the last door does not have open under it. There's no hole under the last door, so it cannot contain or be placed on top of another door. That is the difference between this and the previous 2. So if you look at it again, you will realize that this has a stopping condition such that it gets to a point where the recursion will stop. But in the previous 2 examples, there is no condition for the recursion to stop. Having seen these 3 examples of a real-life recursion operation, let's continue with the next slide. So in this slide, we're asked, what is recursion? Now, recursion is a technique whereby a problem is expressed or represented in a similar or smaller form to the original problem. So that problem is represented in a similar and also smaller, or in a similar but the same form of the original problem. Now, how do you know when to apply this recursion in solving a problem? There are 2 basic things to tell you that a recursion can be used to solve a particular problem. If that problem has stopping condition, then that is one indicator that recursion can be applied to solve that particular problem. Another indicator is if that problem has a recursive step. That is another indicator that the recursion can be used to solve that problem. These 2 conditions are very important in determining if recursion can be used to solve any given problem. We will see examples of this. Now, let's look at the first example here, which is looking at calculating the factorial of a given number n. Normally, if we want to calculate the factorial of an integer or a positive integer n, it goes by finding the product of all the subsequent numbers that comes before that particular number. So for instance, if you want to calculate the factorial of number n, it is equal to n times n minus 1 times n minus 2 times n minus 3 until when n gets to 1. So there are 2 basic conditions in calculating in finding out if recursion can be used to solve a problem. And those two basic conditions are: one, that the problem should have a stopping condition, and two, that the problem should have recursive condition. So looking at these two conditions we have here, where the first one is that n must be greater or equal to 1. And the second one is that if n is equal to 0, then the factorial of 0 is given as 1. If you look at these two carefully, we will see that this second condition is the stopping condition, because once n is equal to 0, then the factorial is equal to 1. Factorial of 0 is equal to 1. The factorial of the number is equal to 1, because the factorial of 0 is equal to 1. But if it is not equal to 0, that means it is more than 1, then the factorial will be expressed as given here. So these are the two conditions, and the two conditions we've seen here are the recursive condition, which is the first one, and the second one is the stopping condition. So this means that we can use recursion to solve this problem. Normally, looking at the example of the factorial of 5 is expressed as 5 times 4 times 3 times 2 times 1, which is equal to 120. It is expressed this way because it goes with this approach. N is given as 5, then we have n times n minus 1, which is 5 minus 1, that gives us 4. And the third one is n minus 2, which is 5 minus 2, is going to give us 3. Then we have the next one, 5 minus 3, which will give us 2. And it continues like that until it gets to 1. So using recursive to define this problem, we first notice that the first condition is when n is greater or equal to 1. So if n is greater or equal to 1, then the factorial will be expressed as this. Otherwise, when n is equal to 0, then the factorial will be given as 1. So like we explained previously, the two conditions that we need to identify if a given problem can be solved using recursion are if the problem has recursive steps and also has stopping condition. So this here is the stopping condition, this recursive steps, and this second one is the stopping condition. Now, the next thing we are going to see is we're going to look at the recursive algorithm. We've seen the two conditions, and how do you represent these using recursive algorithm? To represent it using recursive algorithm, we have to consider the two conditions. The first condition is when n is equivalent to 0. And if that is the case, then the answer is given as 1, because the factorial of 0 is 1. The second condition is when n is more than 0, or then that factorial will be expressed as n times the factorial of n minus 1. So we have represented the stopping case and the recursive case. Now looking at the next one, which is the recursive method. The recursive method is similar to the recursive algorithm, but in this expression, we have to express it in terms of iterative approach, similar to intuitive approach rather. So in this case, we have that the method is n is given as n integer, and if n is equal to 0, then the operation returns 1. Otherwise, the operation continues to calculate n times the factorial of n minus 1. So we can also try to trace the factorial of this recursive algorithm. For instance, let's use this example for finding to trace the factorial of 4. In order to trace the factorial of 4, we have to express this factorial and go down until we get to the ending or stopping condition. We know that the factorial of 4 starts with 4 times factorial of 3. And we continue with factorial of 3 is expressed as 3 times the factorial of 2. The factorial of 2 is expressed as 2 times the factorial of 1. Factorial of 1 is expressed as 2 times the factorial of 0. And we all know that the factorial of 0 is 1. So we have gotten to the stopping case or the stopping condition. So the next thing we need to do is to look back to the starting point of the recursion. So knowing fully well that the factorial of 0 is equal to 1, then looping back, we have it means that it returns the value 1. Then the factorial of 1, it will return the value 1. The factorial of 2 is going to return the value 2. What is happening here is that you take this value and multiply it with 1. For instance, we are going to take this value and multiply it with 2 because we know the factorial of this 1 is 1. Then the next factorial, which is the 3 times factorial 2, having calculated factorial 2 to be 2, then it's going to be 3 times 2, which is 6. The next loop we're going to have is knowing fully well that factorial of 3 is given expressed as 6. Then we're going to say 4 times factorial of 3. Now factorial of 3 is 6, so it's going to be 4 times 6. And we have come to the last point of finding the factorial of 4. So in this case, the result or the answer will be equal to, the final answer would equal to 24. Let's proceed. Here we have an activity that asks us to discuss whether a recursive approach should be used to evaluate an integer. So another question says, is an interactive approach better than recursive approach? Give the algorithm for an interactive solution for the evaluation of an integer, and also analyze the complexity of both interactive and recursive implementation. One thing we have to do is that we need to implement this before we'll be able to analyze both of them and also compare both of them. So I advise you pause this video and take a sheet of paper and write a recursive approach of an integer, and also write a interactive approach of an integer. Study both of them and find out which of them will be better. Is interactive going to be better than the recursive, or recursive going to be better than the interactive? So this is what you are required to do. Another thing I want to remind you, which is kind of a hint, is that for any problem to be solved using recursive, that problem must have stopping end or stopping case. You can also call it stopping condition. And also the problem should also have recursive condition. So if now we have been asked to discuss whether a recursive approach should be used to evaluate an integer, it's left for you to decide based on these conditions that we have stated. And using these two conditions, you have to compare it with interactive approach and know which one will be better. Another thing I want to tell you about the interactive approach, which we will be discussing in the subsequent slide, is that writing interactive approach is similar to using for loop or while loop to perform the repetition of that section of the code that you want to repeat. So for instance, if you want to repeat this n, you can find the stopping case by maybe assigning that whenever n is equal to 1, then the program needs to stop. If that else, then the program will have another condition that will make it to continue to loop. That is a hint, a kind of a hint, which you can use to find the solution to this problem interactively, and also compare it with the recursive approach. Moving on with another example, which is the triangular numbers. In triangular numbers, if we are given a number 1, for instance, assigned to the value n, then that number will be represented with a dot. And the approach is that, for instance, we've been given the sequence of triangular number as 1, 3, 6, 10, 15, 21, 28, 36, and it continues that way to any point that you want to stop. If you look at this very well, you will realize that there is a pattern of increase. And that pattern of increase is very important for you to be able to find out if recursive approach can be used to solve this kind of problem. For instance, when n is 1, it is represented with 1 dot. But when n goes to the second point, it's represented with 3 dots. But when n goes to the third point, it is represented with 5 points, 6 points rather. So there is a pattern of increment in this sequence. And looking at the next slide, we see that the recursive algorithm recursive techniques can be used in finding or providing solutions to this algorithm. For instance, we can say that if number is equal to 1, then it returns value 1. So for instance, here we have that n is equal to 1, and we are calling n number in our own case in the algorithm. So it returns the value 1, and that value 1 is the dot. And that is the stopping condition. If that is not the case, it continues. Why it continues, the operation changes. What will happen in this operation is that it will take the value of n and add it to the prime number, which is n minus 1. So in the case of this one, where we have the value as 3, in the previous slide, we saw the value as 3. So now what is going to happen is that you have, we have the number as 2. So how do we get these 3 dots? You have, if you put 2 here, we have 2 plus, the prime number of 2 is 2 minus 1. So we have 1. So 1 plus 2 will give us this dots 3. Another example is if you use n, or assume that n is equal to 3, implies that n here is 3, and the prime number for 3 is 2. So we're going to find 5 dots. If you do it for 4, you also get this number of dots. Now let's look at how we can find the sixth triangular, trace the sixth triangular number recursively. In order to trace the sixth triangular number, we have to follow the pattern. And the pattern number 1 is that the sixth number will need the fifth triangular number. And the fifth number will need the fourth triangular number. The fourth triangular number will need the third triangular number. The third number will need the second triangular number. We continue like that until we get to the stopping condition or the stopping case, when we might have reached the value 1. So now that we've reached the value 1, we have to recursively trace back to the sixth triangular number. And doing that, we have to add this 1, because the first triangular number is giving us 1. So 1 plus 2 is going to give us 3. Then the second triangular number we have calculated here is 3. So we're going to move 3 to this place. So we have 3 plus 3 will be equal to 6. So in order to calculate this third one, we have already calculated the third triangular number. So in that case, we're going to have 6, move 6 to this place, and 6 plus 4 is going to give us 10. That is how we continue until we get to the end, where we can find the sixth triangular number, and it is given as 21. So the final answer to this, to tracing the sixth triangular number recursively, is going to be 21. I'm moving to another activity, which says that we should write an interactive algorithm to determine the nth triangular number. This is an interactive algorithm. Remember, in the previous ones, what we wrote was a recursive algorithm or recursive approach to determine the nth number. But in this case, we are going to use interactive approach. One thing you have to keep in mind is that the interactive approach, you use conditions like loop and conditions like while loop or for loop. So in this one, we can have the try number initialized to 0, and now have a condition that as long as n is greater than 0, then we'll calculate the try number by saying that try number is equal to try plus the number. And we continue again by adding or going to the next number, which will be assigning number minus 1 to the previous to number. So to explain this further, we have done similar thing we did in the recursive approach. However, in this approach, we used interactive approach instead of recursive approach. Remember again that interactive approach makes use of while and for loop. So this is a solution to this question and asks us to determine the n triangular number of these using interactive algorithm. Now we have another activity here that we're given the recursive method. We've already been given a recursive method in this way. We ask the question which says, what is the output from call of mystery if 4 is assigned to n and 5 is assigned to 4? Now, we have this recursive method given like this. And the recursive method requires input which are integers, n and m. Now, the stopping condition is when n is equal to 0. But the looping or the recursive condition is given as this mystery to be equal to mystery. In bracket, we have n minus 1, then we have m plus 1. So to solve this problem, first you know that n is not equal to 0 because n is given as 4. Then we must have to move to the recursive condition. So to solve it, you may just pause this video and get a paper to work it out. But giving you a clue on what you have to do is that you have to start with the first one, which is the fourth, which is when n is equal to 4 and m is equal to 5. So in this case, we will impute n at this position and m at this position and add 1 to it. So this is the first iteration. Then the second one is when you've removed 1 from 4 and you're going to have 3. So in that case, you're going to have 3 in place of n. and you repeat the operation until you get to a point when n is equal to 0. At that point when n is equal to 0 is when you have your stopping condition. So it is at that point that you have to trace back and come to the level where you started initially. So this is the steps you need to take for you to achieve this, to find the output of this mystery using the value 4 and 5 for n and m. If you have any problem concerning how to resolve this, you can ask during the tutorial section and we will support you during that time. Let's now have a look at another activity. This activity is saying that we have given an array A, and that array contains any number of integers. We are asked to develop recursive algorithm to find the sum of the n integers. And another question is, what is the stopping condition and what are the recursive steps? We also asked to draw a trace of the algorithms for the array consisting of 5 integers. And the 5 integers are given as 4, 3, 6, 2, and 5. So looking at this question, first is that we need to develop recursive algorithm to solve this problem. And remember that the problem is looking at sum, and that sum is going to be summing the integer. And we have to find a way to get the stopping condition and now find another way to get the recursive steps or the recursive condition. So in the next slide, we have a solution to this problem. One is that we are looking for the sum of n number of integers. And that n number of integers is coming from our array. Then we have a stopping condition which says that whenever n is equal to 1, then it returns the array value of that particular number, which is the starting number, because we assume that the array is indexed from 1 to n. So it is going to return the first number. Otherwise, it will continue by finding the sum of n minus 1 plus the previous number, which is a recursive one. And it continues that way until this condition is met before it stops. Now, this has answered the first question, and we have also been able to identify the stopping case and the recursive case. And the next thing we have to do is we've been asked to draw a trace of the algorithm for an array consisting of 5 integers. So, and we have been given that integers. Then for us to draw this, we have to do it this way. So what we are doing is that we are looking at a series of recursive calls to find the stopping case. That is the tracing. For us to find the recursive case, the first operation is when 5, we are looking at the 5th number, which is 5. So for us to get the 5th number, we need so for us to get the sum, we need to follow the condition given in the previous slide. And the condition given in the previous slide is that the recursive approach goes with n minus 1 plus the previous number. So 5 minus 1 is going to give us the sum of 4, and the previous number is 5. Then the second step is that we have to continue with 4, which is 4 minus 1 is going to give us 3, and the previous number is 4. Then the third sum is 3 minus 1 will be 2, and the previous number is 3. And the 2 minus 1 is 1, and the previous number is 2. Then if we perform another operation, which will be 1 minus 1, then we are going to have 0. And at that point, we've reached to the stopping case. So now that we've reached to the stopping case, we have to trace back. In order to trace back, remember we've been given that the first value if we go back to this point, that the first value of the integer is 4, then we have to trace back by saying that this is the first value of the returning number, and we add it to the next one, which is going to give us 7. Then we have to bring up that 7 here and add it to the next one, which is going to give us 13. We take 13 to this point and return 13 to this point and add it to the fourth number, which is going to give us 12, 15 rather. Then we return 15 at this point and add it to the fifth number, which is 5, and we have 20. So at this point, we have the final answer to be 20. This is how we are going to trace the fifth. You're going to trace the fifth number and get the sum. Now, there is another question here, which is looking at finding the reversing element of an array recursively. So we've been given an array of integer, and that integer is contained in an array A. Remember that whenever you have or you want to use, so remember whenever we want to use recursive approach to proffer a solution to any problem, we have to consider the two conditions. So you need to first of all think about what is going to be the stopping case and what will be the recursive step. So if you have these two, then you will be able to find out how you can do the operation in a reverse order. Now, this is a solution to performing the operation in a reverse order. So we have these two variables coming from the array. We assume that I start from the beginning going towards the last point on the array. And we also assume that J start from the last point coming towards to the first point. It's expected that if we are to swap these two items, depending on the conditions we have provided, that if we keep swapping these two items, when I is less than J, then we perform the swap. And if we keep performing the swap, we'll observe that when you came to the middle, when both of them come to the middle, that is J is coming from right and moving to left, and I is coming from left and moving towards right. They will get to a point which will be at the middle when all the elements in the array should already be sorted. So in that case, we have to look at what will be the stopping case and what will be the recursive case. So the recursive case now is when I is less than J, it performs this operation by swapping and putting it in a reverse order. But the stopping case will be whenever J becomes equal to or greater than, I becomes greater than or equal to J, then that will be where the stopping case will happen. So if we continue, we're going to look at the Fibonacci number. And we've been given numbers like these: 1, 2, 1, 1, 2, 3, 5, 8, 13, and 21. So if you look at this number we've been given, you see that the number is increasing in a particular pattern or order. Then it says that the nth Fibonacci number is the sum of the previous two numbers. For instance, if you want to find the Fibonacci number of 3, then it is the sum of the two previous numbers, which is 1 plus 2, going to give you 3. So now, what is the recursive algorithm to determine the n Fibonacci number? So how do you provide a recursive algorithm to determine the n Fibonacci number? Recall that we are concerned about the stopping case and the recursive case. So the first question you have to answer is, what is the stopping case? And the next question you also have to answer is, what is the recursive case? So in the next slide, we have this recursive algorithm. The recursive algorithm has an input n, and that n needs to be considered if it is equal to 1 or is equal to 2. If n is equal to 1 or equal to 2, then it returns 1. So that point is when it is going to stop. Because if you look at this, for instance, when n is equal to 1, you realize that it cannot work with the condition or the terms that Fibonacci number works with, which is that the Fibonacci number of a given number is the sum of the two previous numbers. But this particular given number has no two previous numbers. So that condition to continue with the Fibonacci operation cannot happen on this. Likewise, it cannot happen on this. So when n is 1 or n is equal to 2, we've reached the stopping case. But if n is greater than that, then the Fibonacci will be operated by using the Fibonacci number of that n minus 1 and plus the Fibonacci number of n minus 2. So we have to look at the Fibonacci number and the observation. What do you observe in the Fibonacci number? If you go through your the module, you see some solutions that we have provided on interactive operation, using interactive operation. So one thing is that the interactive operation requires little addition when compared with the recursive operation or techniques. For instance, in the interactive operation of calculating the nth Fibonacci number, it requires n minus 2 additions. But using recursive approach, it requires n Fibonacci number minus 1 addition. So if we have a look at this example, we want to calculate the 30th Fibonacci number using interactive and recursive approach. For interactive approach, is going to be n minus 2 addition, which is n, our 30, which is 30 rather, minus 2. And n 30 minus 2 will give you 28 addition. However, the recursive approach, we need the nth Fibonacci number of that given number minus 1. So this is the Fibonacci number of 30 minus 1 will give us 832039. So you see that there are a lot of addition when using Fibonacci number compared to the number of additions where you will get if you are using interactive solution. So why do we have these Fibonacci unnecessary additions in recursive solution? Let's have a look at this cost of recursion. The cost of recursion will give us an idea how the unnecessary additions came about, happened in a recursive using recursive approach. Now we want to trace the Fibonacci number 6. So we know that Fibonacci number 6 requires Fibonacci number 5 and also Fibonacci number 4. And Fibonacci number 5 requires Fibonacci number 4. Sorry, Fibonacci number 5 requires Fibonacci number 4 and Fibonacci number 3. Likewise, Fibonacci number 4 needs Fibonacci number 3, and subsequently we need Fibonacci number 2. And also Fibonacci number 3 will need Fibonacci number 2 and Fibonacci number 1 before you get to the stopping end. Now, if you look at this, you realize that there are repetitions of Fibonacci everywhere. For instance, we have 4 repeated itself twice, and we have 3 repeating itself 3 times, and we have 2 repeating itself so many times. So it is because of this continuous repetition of Fibonacci numbers, while calculating the Fibonacci number for that particular, by calculating the Fibonacci number of that particular number using recursive approach, that makes it less efficient when you compare it with the interactive approach. And this increases the number of addition as well. So we've said earlier that the recursive approach could be a very good way to perform or provide solutions to any given problem. But one must be careful while choosing the recursive approach. Though it is compact and elegant, but you must be very careful before you decide to use recursive approach to solve any given problem. Now, let's look at the pitfalls of recursion. So we said recursion before you use recursion, you must be careful and must make sure you understand that recursion can be used, and also that recursion is the best approach to use to solve that problem. As it says, that recursion can be it is possible to write compact and elegant recursive program that fails spectacularly at runtime. So that's the problem with using recursion. Then the main pitfall are the first one is forgetting the stopping case. If you forget the stopping case, then the recursion the recursion will introduce a problem in that particular algorithm. And another thing is when it fails to reach the stopping case. So if it fails to reach the stopping case, that is also going to be a problem. You know, in the real life story we told about the captain, you saw that there was a series of recursion happening, and there was no stopping case at all. So, but in the case of the Russian door, we also saw that there was a stopping case. But what if that stopping case, which is the smallest door, was removed and replaced with other doors? Then we see that it will fail to reach the stopping case. Another thing about recursion is that it takes excessive space. That it takes a lot of space. We saw it in the diagram we explained in the previous 2 slides or thereabout. And we also know that it requires a lot of computational time. So if these things are not, these are the pitfalls of recursion. Then when do we use recursion and when do we not use recursion? So if these answers to these questions are no, then you don't have to use recursive approach. First, you have to ask this question: is the algorithm or data structure naturally suited for recursion? If it is no, then you don't have to use recursion. Is the recursive solution shorter and more understandable? If the recursive solution is not shorter and is not more understandable, then we do not have to use recursive solution. Does the recursive solution run in an acceptable time limit or space limit? So if the recursive solution does not run in an acceptable time limit and it occupies a lot of space, then it is not advisable to use the recursive method in solving that problem. So this is where we are going to end today's session. But before we end the session, we want to let you know that this particular workshop is very important because it is talking about recursion, and it is very important as it is talking about recursion, which will be used in the subsequent lectures. So we advise that you make sure you understand the techniques of recursion and also understand the difference between interactive and recursive techniques. You also need to go through the lectures and carry out all the examples, consider them and look at them, and also work out the exercises. So try and attempt the exercises. If there's any problem you encounter during the time you are working on the exercises, please let us know during the tutorial section or book a drop-in session, and we will discuss that with you. Thank you so much and see you next time. Bye.